Imagine a severe storm hits your city.
Mm.
You know, you are standing in the municipal command center.
Right.
The wind outside is howling. The rain is torrential. And then the inevitable sequence of cascading failures just begins. The main power grid trips and goes totally
It
down.
always happens.
Yeah, it always
Yeah.
does. The backup generators kick in, but a few minutes later, the cell towers in your district begin to drop offline, like one by one as their own batteries flood or drain.
Yeah.
Your internet access is completely severed.
It's gone.
Gone. Whether it is the primary fiber optic line buried under the street or the mobile data network, it does not matter. You are plunged into a total communications blackout.
Which is terrifying.
It really is. In that specific moment, how do citizens in your community call for help?
Yeah.
I mean, if a family is trapped by rising floodwaters 3 streets over, how do they signal their location?
They really can't.
Right. How do you, assuming you are the local leader or decision maker listening to this,
Mhm.
and you're tasked with their safety, how do you coordinate rescue efforts when you cannot even send a basic text message to the neighborhood next door?
Yeah, for the vast majority of modern governments, from tiny rural municipalities to massive urban metropolises, the terrifying reality is that they simply cannot.
It's a complete failure.
It is. It exposes a profound and, well, systemic vulnerability in how we have structured public safety. Over the last 2 decades, we have built our entire society, our emergency response protocols, and our daily governance on the underlying assumption that the global internet is a permanent, indestructible fixture.
Like it's always going to be there.
Exactly. We treat digital connectivity like oxygen. We expect it to just flow. But in a disaster, that oxygen is often the very first thing to get sucked out of the room. When the cloud disappears, localized coordination completely collapses because, the physical architecture of modern technology dictates that your device must talk to a server thousands of miles away just to communicate with the person sitting across the street.
Which is crazy when you think about it. And that brings us to the core mission for today's deep dive. We are exploring a completely revolutionary blueprint for what we are going to call offline-first community resilience.
It's a game changer.
It really is. It is a Philippine-designed architectural framework known as Project Bantay Bayan, or PBB.
Yeah.
Right out of the gate, we need to draw a hard line here. We are not talking about some new emergency app that you just ask citizens to download on the App Store.
Yes, definitely not.
We are unpacking a total, fundamental rethinking of digital public infrastructure. This exploration is custom-tailored for you, whether you are a decision maker, a policy maker, a lobbyist, or a municipal leader trying to figure out how to keep a community functional when the broader grid fails.
The central shift in philosophy here actively challenges the prevailing dogma of the tech industry. I mean, the relentless trend in IT and governance has been centralization.
Everything moves to the cloud.
Yes. The directive has been to move everything up, to consolidate compute power in massive hyperscale data centers located in seismically stable regions far away from local hazards. PBB actively rejects that premise for emergency services.
Because if the local connection is cut, those safe data centers are useless to you.
Exactly. Instead of forcing a vulnerable community to rely on a distant cloud server over fragile fiber lines, this architecture brings the cloud directly into the local neighborhood.
It essentially mandates that if the physical disaster is local, the digital response infrastructure must also be local. It is a localized node architecture.
Yeah, the objective is to keep essential civic services running smoothly on localized, isolated networks, even when the rest of the world goes entirely dark. Services like emergency reporting, geographic mapping, health coordination, and community messaging.
It acts as the ultimate digital safety net. But to truly understand how you, as a leader, can procure, deploy, and justify this kind of resilience to your constituents or your finance committee, we have to examine the entire logistical and technical stack.
We really do.
We need to start with the physical hardware, so the literal machines sitting in a local community center. Then we have to examine the network architecture, meaning the digital roads connecting the community to those machines.
And the software ecosystem, too.
Right, the software acting as the traffic on those roads. Finally, we have to break down the economic and procurement model that makes this system auditable and sustainable without bankrupting a local government unit.
It operates as a deeply interdependent ecosystem, You cannot appreciate the ingenuity of the software until you understand the physical constraints and the hardware foundation it is forced to operate upon.
So let's ground this in physical reality. If you are a local leader, say you are a Barangay captain in the Philippines, a county commissioner in the American Midwest, or a mayor anywhere else in the world, what is actually sitting on the desk in your neighborhood hall?
Good question.
If we are bringing the cloud home, what does that physical footprint look like?
Well, in the very early experimental pilots of this technology, deployments usually relied on just a single machine. It was one compact computer attempting to route the network, host the database, serve the maps, and run the chat applications simultaneously.
Like an all-in-one box?
Yeah, exactly. However, as the PBB blueprint matured and faced the realities of actual crisis deployments, the engineers realized that for life-saving operations across an entire community, relying on a single machine introduces an unacceptable single point of failure.
Makes sense.
Consequently, the architecture now strictly mandates a three-machine standard. It requires three physically distinct pieces of compute hardware to form a local cluster.
Okay, I have to challenge that requirement from a pure procurement and IT management perspective. If you are staring at a municipal budget right now, buying three separate machines seems counterintuitive.
I get that a lot.
Right. In the modern era of computing, one single high-end server can run dozens of virtual machines. You can buy one robust box, partition the hard drive, use a hypervisor to separate the workloads virtually, and save a massive amount of money on physical hardware, power supplies, and rack space.
That is the standard enterprise argument, yes.
So why force a local government to buy and maintain three physical boxes when software virtualization exists?
Because virtualization is incredibly efficient for enterprise cloud environments, but it completely fails to address the unique physical hazards of a localized disaster node.
How so?
Well, when you use virtual machines on a single physical server, they still share the same physical motherboard, the same memory bus, the same network interface card, and the same physical CPU cache.
Right. The physical hardware is all shared.
Yeah. So if a sudden, massive surge in user traffic causes a memory leak or a catastrophic bottleneck, meaning the system is trying to read and write data faster than the physical hardware can process, the hypervisor itself can crash.
Oh, wow.
And when that happens, every single virtual machine goes down simultaneously. In disaster resilience, you have to prioritize isolation over efficiency. This introduces a critical concept from site reliability engineering that decision makers must grasp. We call it the blast radius.
The blast radius. So we're not talking about physical explosion here, but the cascading digital damage if a single application or process spirals out of control.
Exactly that. The blast radius is the maximum potential impact a single failure can have on the broader system. So imagine you have a single server running everything.
Okay.
You have your critical emergency hotline, your offline maps, your dispatch database, and then you have a community chat room and a digital learning module for local kids.
Right.
What happens if, during a severe storm, 2,000 panicked citizens suddenly log into the community chat room to ask about the power outage? The CPU usage spikes to 100%, trying to route thousands of messages a second.
So the physical processor maxes out, which means the emergency hotline running on the same processor is suddenly starved of compute resources. It slows down or crashes entirely.
Exactly. The emergency services vanish at the exact millisecond they are needed most. By mandating a strict three-machine standard, PBB physically air gaps these workloads at the hardware level.
Oh, that makes so much sense.
Yeah, you contain the blast radius by ensuring that a spike in casual community traffic physically cannot steal processor cycles from the emergency dispatch system.
That makes the hardware mandate much easier to justify to an auditor. So let's break down the actual division of labor across this trio. What is Machine 1 doing?
Machine 1 functions as the core server. It is the absolute brain and traffic director of the local operation. Its primary responsibilities are identity management, core database synchronization, system monitoring, and authorizing node access.
So it's mostly working behind the scenes.
Yes. It operates mostly in the background. It does not interface heavily with the public directly. Instead, it ensures the node is healthy, authorized, and that user credentials are valid.
It maintains the structural integrity of the localized network.
Got it.
And Machine 2?
Machine 2 is the emergency and operations server. This is the shield. This specific piece of hardware is strictly dedicated to critical life and death workflows.
So this is where the real emergency stuff happens.
Exactly. It handles the citizen emergency reporting interfaces, the incident handling dashboards for local operators, the real-time command workflows, and the generation of structured situation reports. Crucially, it also handles the offline map rendering and spatial database queries.
Wait, so if a flash flood hits, Machine 2 is the hardware actually processing the SOS signals and rendering the offline map for the rescue teams.
That's right.
And because it is a separate physical computer, no matter what else is happening in the neighborhood, it has 100% of its processing power dedicated exclusively to those rescue workflows.
Yes, that physical isolation guarantees performance. Finally, we have Machine 3, which is the daily app server. This operates as the engagement engine for the community.
The engagement engine.
Yeah, it runs the local chat applications, the gamified offline learning modules, the local health center scheduling interfaces, and public bulletin boards.
Okay, at first glance, a finance committee might look at Machine 3 and flag it as non-essential.
Hmm.
I mean, why are we funding a server for community chat and games when we're trying to build an emergency response network?
It seems backwards, right? We will explore the deep psychological reasons for this when we discuss the software layer, but from a hardware perspective, Machine 3 is the lightning rod.
The lightning rod. I like that.
It is designed to absorb all the chaotic, high-volume, unpredictable civilian traffic. It actively encourages citizens to use the local network every single day.
But what if it gets overwhelmed?
Well, if that daily engagement suddenly spikes and overwhelms the system, Machine 3 might lag or require a reboot. But because of the 3-machine standard, Machine 2, the emergency server, remains completely unaffected.
Oh, wow. So the rescue teams do not even notice the localized traffic jam.
Exactly.
It is analogous to constructing a physical highway with a dedicated concrete-separated lane exclusively for ambulances. It doesn't matter if the civilian lanes are backed up for 10 miles, the ambulance will always maintain top speed because it is operating on entirely distinct infrastructure.
That analogy captures the engineering intent perfectly. When you are a decision maker defending this budget, you are not buying 3 computers out of extravagance. You are paying for hardware-level insulation to guarantee that your emergency response system cannot be compromised by everyday digital traffic.
We have established the necessity of this 3-machine cluster. However, the physical reality of a jurisdiction varies wildly.
It really does.
The hardware required to serve a hyper-dense high-rise downtown district cannot possibly be the same hardware required to serve a remote, sprawling mountainous village. How does the PBB architecture adapt to extreme geographic and demographic differences?
The blueprint utilizes a highly structured tiering system that scales based on population density, total land area, and local topography. It is important to look at this in relative investment terms, as strict monetary figures fluctuate wildly with global supply chains.
Right. Prices change, but the ratios remain constant.
Exactly. The tiering ensures you are not over-engineering a small village or underpowering a major urban center.
Let's walk through the deployment scales.
The absolute baseline is Tier 0, which we call the compact node. This is a highly constrained, ultra-low-cost, single-machine setup.
Wait, I thought you just said no single machines.
I did. It is critical to state clearly that Tier 0 is explicitly forbidden for real-world whole-community deployment. It violates the 3-machine rule.
Okay, so what is it for?
It exists strictly for indoor lab tests, software demonstrations, or controlled proof-of-concept setups inside a single conference room. It represents a minimal capital expense just to prove to stakeholders that the software framework actually functions.
It is the test drive. You would never deploy a Tier 0 to actually handle a hurricane response.
Never. The true operational starting point is Tier 1, the standard node. This is the baseline 3-machine cluster designed for an average-sized, relatively centralized neighborhood.
What does that look like in terms of cost?
You have your core, operations, and daily app servers running on robust mini-PCs paired with standard network routing gear. The investment here represents a moderate capital expense that is highly affordable and easily justifiable for a standard local government unit.
Okay, let's apply this to a real-world edge case from our sources. There is a case study regarding a specific area in Danao City, Philippines, called Sabang. The geographic data paints a very specific picture. Sabang has a tiny physical landmass, but an incredibly dense population. You have over 16,000 people crammed into a highly constrained physical space.
Yeah, Sabang is a great example. A demographic profile like Sabang requires Tier 2, the dense urban node. What is vital to understand here is that the central compute power, the 3 server machines themselves, does not need to change drastically from Tier 1.
Wait, really? With that many people?
Well, really, you might upgrade the RAM to handle larger databases, but the primary shift in capital investment goes almost entirely into heavy-duty networking gear.
Oh, because they're all trying to connect at once.
Exactly. In a dense urban area, the physical distance the Wi-Fi signal needs to travel is short, but the volume of simultaneous connections is massive. During a crisis in an area like Sabang, you could have 5,000 citizens in a 2-block radius simultaneously pulling out their phones to connect to the local node.
And standard routers would just die.
Standard routers will instantly melt under that kind of connection request load. A Tier 2 investment focuses on enterprise-grade, high-capacity access points and advanced switch fabrics capable of managing thousands of concurrent IP leases without dropping packets.
So the hardware investment shifts from compute to traffic management.
Precisely.
But what about the exact opposite scenario? Another Danao City example in the sources is the Bayabas area. It presents a totally different logistical nightmare, like a massive, sprawling landmass covering over 14 square kilometers, featuring rugged upland terrain, but containing a highly dispersed population of only a few hundred people.
Yeah. Bayabas necessitates Tier 3, the resilience node. This is the premium, heavy-duty architectural setup. In Bayabas, the network is not going to crash because of connection volume, because you only have a few hundred people.
Right.
The existential threat is distance, environmental hostility, and total power isolation. A Tier 3 capital investment heavily prioritizes outdoor network links. You have to purchase high-gain directional antennas to beam the network signal across deep valleys or through dense foliage.
Because you can't just run an Ethernet cable through the jungle.
Exactly. Furthermore, a remote upland area like this might lose connection to the primary power grid for weeks, not just hours. Therefore, a massive portion of the Tier 3 budget must be allocated to environmental hardening, so things like heavy-duty solar arrays, advanced battery banks, and portable generator support. You are essentially building a self-sustaining digital outpost.
Wow, it really underscores why generic, one-size-fits-all IT procurement completely fails in public service. If you deployed a Tier 2 setup in Bayabas, the routers would be incredibly fast, but the signal wouldn't reach past the first hill, and the whole system would die after 2 hours without grid power.
And if you deployed a Tier 3 setup in Sabang, you would have incredible solar power, but the routers would crash the moment 3,000 people tried to log in simultaneously. The infrastructure must mirror the geographic and demographic reality.
So logical. Is there anything above Tier 3?
Finally, above all of these is Tier 4, the city or municipal support node. This is not designed to serve citizens directly in a single neighborhood. It is an aggregate master node.
Where does that sit?
It physically resides at the mayor's office, the central police headquarters, or the city's primary command center. Its purpose is to sit above the fray and pull data asynchronously from all the localized Tier 1, 2, and 3 nodes distributed across the surrounding districts. It acts as the ultimate centralized coordination hub for the macro-level response.
We have established an incredibly robust physical foundation. We have our 3 machine clusters scaled perfectly to their environments, whether that is a dense urban block or a rugged mountainside. But this hardware isolation introduces a massive logistical problem.
What's that?
Having 3 powerful machines safely humming away inside a reinforced neighborhood hall is completely useless if the citizens shivering in an evacuation center 3 blocks away cannot talk to them.
Very true.
We have to physically bridge the gap between the citizen's smartphone and the local server when the commercial internet is completely dead. How do you construct the digital roadways that make this localized cloud accessible?
This requires a deep dive into the network architecture. For a local leader or policymaker, you have to undergo a paradigm shift because you are no longer just buying computers. You are effectively building and operating your own localized internet service provider, or ISP. You are laying down a bespoke digital roadway.
So what are the physical components of that local roadway?
It requires a specific chain of specialized networking gear. It begins with a heavy-duty enterprise-grade router. This acts as the master traffic controller for the entire local network, assigning internal IP addresses and routing data safely between different devices.
Okay, standard networking so far.
Right. Connected to the router, you have managed network switches. These act as the physical intersections that connect your 3 servers together, allowing the core, ops, and daily apps machines to communicate securely at gigabit speeds. But the most critical piece for deployment logistics is the requirement for Power over Ethernet, or PoE, switches.
Power over Ethernet. Let's translate the importance of that for a decision maker who is focused on deployment speed and labor costs. Why does PoE matter so much in a post-disaster or resource-constrained environment?
Well, if you are relying on standard networking equipment and you want to mount a Wi-Fi antenna on the exterior roof of an evacuation center to provide coverage to the surrounding courtyard, you face a labor problem.
Which is?
You have to run a data cable from your server room up to the roof to provide the network signal. But an antenna also requires electricity. This means you must hire a licensed, specialized electrician to run a high-voltage power conduit and install a weatherproof electrical outlet on the roof right next to the antenna.
Oh, I see.
Yeah, in a post-disaster scenario or in an underfunded municipality, finding an available electrician and securing high-voltage permits can delay deployment by weeks.
It creates a massive logistical bottleneck.
Power over Ethernet completely eliminates that bottleneck. A PoE switch injects low-voltage DC electrical power directly into the standard copper network cable alongside the digital data.
Wait, really? Both power and data in one wire?
Yes. This means a single, inexpensive network cable carries both the data signal and the electricity required to power the antenna.
So a standard IT technician, or even just a trained local volunteer, can simply run one single wire up the wall, plug it in, and the system is live. No electrician required.
Exactly. It makes physical deployment infinitely faster, dramatically cheaper, and significantly safer because you are not dealing with exposed high-voltage lines in potentially wet or damaged environments.
So we have the router, the managed switches, and these single PoE cables running out of the server room. How does that localized signal actually interface with a citizen who is standing in the rain holding a standard commercial smartphone?
The network is broadcast through access points, or APs. For a standard Tier 1 neighborhood setup, you would deploy a mix of indoor and outdoor access points.
Like a normal Wi-Fi router.
Yeah, they broadcast a standard Wi-Fi signal just like the one you have in your house or at a coffee shop, blanketing the Barangay hall, the local health clinic, or the designated evacuation center. A citizen simply opens the Wi-Fi settings on their phone, selects the local PBB network, and their device connects directly to the local router and subsequently to the 3 local machines.
That solves the problem for people physically near the neighborhood hall. But what if the critical infrastructure is spread out? Referring back to the Bayabas area example, what if the local government unit's server room is in the valley, but the primary evacuation center is located 2 kilometers away on a ridgeline, separated by dense forest?
Right.
You cannot run a 2-kilometer Ethernet cable through a jungle.
No, you can't. In those scenarios, you utilize point-to-point, or PDP links.
Sure.
These are specialized, highly directional microwave antennas. Standard Wi-Fi access points are omnidirectional, meaning they broadcast a signal in a 360-degree circle for nearby phones to catch. A point-to-point link does not broadcast to phones. Instead, it takes the local network data and shoots a highly focused, concentrated beam of radio frequency directly at a paired receiving antenna located far away.
Assuming you have line of sight, you can basically beam the local network across massive physical obstacles.
You can beam a gigabit network signal across a deep valley, over a flooded river, or across a bay to a neighboring island, sometimes over distances of 5 to 10 kilometers or more.
That is incredible.
So you can keep your 3 delicate server machines safely locked in the reinforced municipal building and use a point-to-point link to instantly extend that localized network to a remote health clinic on the other side of a mountain.
It essentially functions as an invisible digital fiber optic cable suspended in the air.
It dramatically extends the physical reach of your local cloud without requiring the massive capital expenditure of digging trenches and laying physical cables.
The physical broadcast mechanisms are super clear now. But this brings up a major, often overlooked usability hurdle that anyone who has tried to use a hotel Wi-Fi network understands.
Oh, the dreaded captive portal issue.
Well, exactly. Normally, if the broader internet goes down, modern smartphones become incredibly frustrating. If you connect to a Wi-Fi network that doesn't have an active gateway to the global internet, Apple iOS or Android will immediately throw an error.
Right, they complain right away.
It will pop up a screen saying no internet connection available, or give you a timeout error, or prompt you with a captive portal that fails to load. In a disastrous scenario, a panicked citizen is not going to open a command prompt and type in a complex string of local IP addresses like 192.168.1.152 just to reach the emergency page.
Definitely not.
If they get a no internet warning, they will assume the system is broken and just give up. How do you seamlessly onboard a citizen into an offline network?
This touches on one of the most critical pieces of hidden network intelligence in the PBB architecture. You can never, ever require a citizen to memorize an IP address or fight their phone's operating system during a crisis. To solve this, the architecture mandates the inclusion of a localized DNS server.
A DNS server. Let's unpack the mechanics of this for leaders who need to understand why this specific software component is non-negotiable.
To understand the local solution, we have to understand the global system. DNS stands for Domain Name System. When you have normal functional internet access and you type a human-readable website name into your browser, like google.com or pbb.ph, your browser doesn't actually know where that is.
Right. Words don't mean anything to a network.
Exactly. It sends a request to a massive global DNS server out in the cloud, which acts like an automated directory. That global server translates the human word into a numerical IP address and directs your phone to the correct server.
But when a disaster severs your connection to the global internet, you lose access to that global directory.
Yes. Your phone asks, where is pbb.ph? And because it cannot reach the cloud, the request times out, resulting in the dreaded page not found error.
So how does PBB intercept that failure?
PBB runs its own highly localized DNS server directly on the local core machine. It acts as an authoritative local directory. When a citizen connects to the local emergency Wi-Fi network, the router automatically assigns this local DNS server to their phone.
Oh, that's smart.
Yeah. Now, when the citizen opens their browser and types pbb.ph, the request never attempts to travel out to the dead global internet. The local DNS server instantly intercepts the request, says, I know exactly where that is, and routes the citizen's browser directly to the local web server sitting on machine 2 in the next room.
It completely bypasses the need for global resolution. It essentially spoofs the process, tricking the phone into functioning smoothly within a closed loop.
It creates a totally frictionless user experience. The citizen does not need to understand network topology or know that the global internet is down.
Which is huge.
Right. They do not need to download an application from the Apple App Store or Google Play Store, which would be physically impossible anyway during a communications blackout. They simply connect to the open Wi-Fi, type a simple, memorable URL, and the local DNS server instantly loads the emergency dashboard. It lowers the technical barrier to entry to absolute zero.
That level of seamless routing is brilliant, but all of this advanced network intelligence, all of these PoE switches, directional antennas, and automated DNS routing protocols, they're fundamentally dependent on physics. If the power drops, the digital roadway simply vanishes.
Network architecture is entirely meaningless without a corresponding power architecture.
If the router loses power for even a second, the entire community loses access to the 3 servers, even if the servers themselves are still running.
Exactly. This is why uninterruptible power supplies, or UPS systems, alongside portable power stations, are strictly mandatory line items in the PBB blueprint. A UPS is a specialized rapid response battery backup system.
So it bridges the gap.
Yeah, the millisecond the main electrical grid drops or fluctuates, the UPS instantly takes over the electrical load without a single microsecond of interruption, keeping the servers, the switches, and the access points alive.
So you don't even see a flicker.
None. If you are a decision maker authorizing the budget for this system, you must internalize the reality that funding the battery infrastructure is equally as important as funding the compute infrastructure.
I imagine it scales too, just like the compute tiers.
Oh, absolutely. For Tier 1 and 2 setups, robust UPS systems might provide enough bridge power to survive until local generators are fueled and started. For remote Tier 3 setups, the power architecture must scale up dramatically to include large-capacity solar arrays and deep-cycle battery banks to ensure the network can run independently for weeks on end.
It is the literal lifeblood of the operation. Okay, let us synthesize where we are, because we have constructed a truly formidable physical setup.
We really have.
We have a secure facility housing a blast radius insulated 3-machine cluster. We have built a robust battery-backed network of routers, PoE-powered antennas, and point-to-point links beaming a localized Wi-Fi signal across the jurisdiction. We have built the physical roads and the vehicles. Now we must examine the actual traffic. What specific workflows are running on these machines?
This transitions us into the software ecosystem. We frequently refer to PBB broadly as an architecture, but what actually executes on those local servers is an entire self-contained city of applications.
I want to focus on the development philosophy here because the source material emphasizes that PBB is built upon a highly robust software framework. Why is that distinction important? Why not just code one massive all-encompassing PBB app that does everything?
Building one monolithic application is a trap that many government IT projects fall into, and it severely limits long-term viability.
How so?
Well, when you build a monolith, every feature is deeply entangled with every other feature. If you want to update the community chat feature, you might accidentally break the emergency dispatch database.
Oh, that sounds like a nightmare.
It is. PBB avoids this by utilizing an enterprise-grade software framework as its foundational layer. This framework handles all the heavy lifting, so things like secure database migrations, advanced queue management, complex routing, and session security. On top of this rock-solid foundation, the PBB developers build modular applications.
So the different functions operate as independent modules plugged into the main framework.
Precisely. It provides unparalleled stability and upgradability. It is the difference between casting a house out of a single solid block of concrete versus building it out of standardized interlocking bricks.
I like that analogy.
Yeah, if the development team invents a better health scheduling module 2 years from now, they can simply swap out that specific brick without needing to rewrite or endanger the core emergency hotline module.
That makes long-term maintenance significantly cheaper and less risky. So let's walk through the actual modules in this digital city. What constitutes the core infrastructure layer?
The first two core applications are landing and account. These constitute the absolute foundation of the user experience.
I assume landing acts as the digital front door.
It does. When the local DNS server routes your browser to the node, landing is the application that serves up the optimized, highly intuitive dashboard. It provides the visual interface showing the citizen exactly what local services are currently available and online.
And count.
Directly tied to this is the account module, which functions as the single sign-on or SSO system. It provides identity management for the offline node.
Why is a unified account system so critical?
Because you need role-based access control across a chaotic environment.
What do you mean by that?
The account module ensures that whether a standard citizen is logging in to report a downed power line or a chief medical officer is logging in to access sensitive medical supply inventories, they are using one secure, locally verified digital identity. The system instantly knows who they are, what their permissions are, and what dashboards they are authorized to see, all without needing to ping a cloud-based authentication server like Google or Microsoft.
Once a user is authenticated through the front door, they need spatial awareness. In any disaster, a flood, a wildfire, an earthquake, knowing exactly where things are happening is paramount.
Oh, definitely.
But the immediate problem is that if the internet is down, commercial mapping applications like Google Maps or Apple Maps become completely useless. If you open them offline, you just see a blank gray grid or a blurry pixelated screen. How does PBB solve the mapping crisis?
This is handled by the map server module, and it is arguably one of the most vital engineering achievements within the PBB architecture. Map server serves up highly detailed interactive map tiles and local boundary overlays, but it achieves this entirely locally, without requiring a single byte of data from the global internet during an emergency.
Okay, the technical mechanics of that are daunting. Geographic map data, especially high-resolution satellite imagery, is incredibly massive. You're talking about terabytes of data for a single province.
Yes, huge amounts of data.
If I have a Tier 1 standard node with limited hard drive space, how on earth is it storing enough map data to be useful?
That is the genius of the deployment strategy. PBB does not attempt to store a map of the entire world or even the entire country.
Oh, it localizes it.
Exactly. During the initial commissioning phase of the local node, when the system is first installed and normal internet access is available, the map server module securely connects to the cloud. It downloads and permanently caches highly specific compressed vector map tiles, strictly limited to that specific neighborhood's exact geographic boundaries, along with customized overlays denoting local evacuation centers, flood zones, and critical infrastructure.
It effectively downloads a hyperlocal digital atlas and locks it inside Machine 2.
Yes, exactly. So 6 months later, when a typhoon hits and the global internet vanishes, the map server is already fully armed. If a rescue coordinator needs to zoom in and see the exact street topography of a flooded subdivision to plan a boat route, the map renders flawlessly and instantaneously because the spatial data is being pulled from the hard drive in the next room, not from a server farm halfway across the globe.
For a local disaster response coordinator, that represents the difference between operating completely blind and maintaining total granular situational awareness. That's incredible. What else operates at this core infrastructure layer?
The real-time server. This is the background engine that handles live event processing and data pushing.
In a standard cloud app, if I send a message, it goes to a server, and the server pushes it to your phone using WebSockets or long polling. How does this work locally?
It uses the exact same advanced WebSocket technologies, but localized. If a citizen submits an emergency report or a commander dispatches a medical team, the real-time server instantly pushes that status update to the screens of every authorized user across the local Wi-Fi network simultaneously.
So no refreshing required.
Exactly. Nobody has to manually hit the refresh button on their browser to see new data. It makes the offline localized system feel just as fast, modern, and responsive as the best enterprise cloud applications.
That sets a powerful foundation. We have identity, we have spatial awareness, and we have real-time data synchronization. Now, we must examine the crown jewel of this system. This is the primary reason decision makers fund this architecture, the emergency anchor, commonly referred to as the Hotline app.
The Hotline app is where theoretical resilience translates into actual saved lives. It is a comprehensive, multi-tiered incident management system. The brilliance of Hotline is that its user interface dynamically transforms based on the role established by the account module.
Let's walk through those roles. How does it look for a regular citizen?
For standard citizens, Hotline presents a highly simplified, panic-proof interface. It allows them to quickly categorize an emergency, so medical, fire, flood, security, pinpoint their exact location using the offline map server, and submit a report or a photograph of a blocked road with massive intuitive buttons.
It minimizes cognitive load when the user is terrified. But what happens when that report reaches the local command center?
When an authorized local operator logs in, these are the personnel sitting at the desks in the neighborhood hall, the Hotline interface transforms into a full-scale incident workbench.
Oh, like a dispatch screen.
Exactly. They see a real-time feed of incoming citizen reports. They can view live locations on the offline map, communicate directly with the reporting citizen, dispatch local response teams, and track the status of physical resources like boats or ambulances.
And what if you were in charge of the whole city?
Furthermore, if you log in as command, say, the mayor, the chief of police, or the head of the disaster risk reduction office, the interface transforms again into a high-level strategic dashboard. You see macro trends, heat maps of incident clusters, and most critically, you possess the ability to generate automated site reps.
Site reps. Situation reports. The absolute lifeblood of bureaucratic coordination and emergency funding.
Correct. During a major disaster, higher levels of government, the provincial or national agencies, desperately need structured, accurate, quantitative situation reports to determine where to deploy national military assets or how to allocate relief funds. PBB's Hotline app aggregates the localized data and generates these comprehensive ITREPs automatically, removing the administrative burden from local operators who are busy trying to save lives.
This brings us to a massive, glaring logistical paradox.
I think I know where you're going with this.
I need to push back hard on this workflow because we have hit a wall here. You have built an incredible local system. The citizens are reporting floods over the local Wi-Fi, the operators are dispatching local boats, and the mayor is generating highly detailed site trips on the local server.
Right.
But the entire premise of this architecture is that the global internet is completely dead. The fiber is cut, the cell towers are down. How on earth does the local mayor actually transmit that site trip to the national government? Creating a beautiful report on a local server that cannot talk to the outside world is like meticulously writing a cry for help, sealing it in an envelope, dropping it in a severed mailbox, and just praying a mail carrier magically appears.
That is the ultimate critique of localized systems, and it leads us to what is arguably the most sophisticated and magical piece of software in the entire PBB ecosystem, the Relay app.
The Relay app.
Yeah, Relay is the engineering solution to the mailbox problem. It utilizes a highly resilient networking technology known as store and forward architecture.
Store and forward. Break down the actual mechanics of how this solves the transmission paradox.
Let us trace the workflow. The mayor generates a critical SI trip detailing casualty numbers and supply shortages on the local node. They hit send, intending it for the national headquarters. The Relay app intercepts this action. It knows that the upstream internet connection is currently dead.
Okay, so it stops it.
In a standard cloud application, hitting send without internet would result in a fatal timeout error, and the data would simply be deleted or lost. The user would be forced to keep trying manually. Relay does the opposite.
What does it do?
It accepts the site trap, heavily encrypts the payload, and securely stores it in a localized transmission queue on the hard drive. It essentially acts as a holding pen. It queues up every incident report, every resource request, and every vital piece of administrative data generated by the local node.
Is securely holding all the envelopes in the mailbox.
Yes, but Relay is not passive. Once data is in the queue, Relay begins constantly, silently probing the external network interfaces for any sign of connectivity.
Okay, I see where this is going.
Now, imagine the chaos of a disaster zone. The primary fiber lines are gone, but maybe a national telecom company drives a mobile cellular truck to the top of a nearby ridge for testing. Or perhaps the damaged local cell tower manages to reboot on backup power for just 30 seconds before the generator stalls again. You get a brief, incredibly fragile blip of a cellular signal.
We are talking about a single bar of unstable 3G or LTE data that exists for maybe 10 seconds before vanishing.
Exactly. A human operator staring at their phone would never be able to open an email app, attach a file, and hit send fast enough to utilize that 10-second window. But the Relay app operates in milliseconds.
Wow.
The exact microsecond the Relay app detects that blip of connectivity, it violently fires the highest priority queued data upstream to the central PBB hub HQ in the cloud. It does not wait for a human to approve the transfer. It automatically and securely forwards the payloads.
Wait, but what if the signal is so fragile that the connection drops halfway through transmitting a large ASCII file? Does the file corrupt and require starting over?
This is where advanced asynchronous queuing comes in. Relay tracks the exact packet transmission. If the connection drops midway, Relay remembers precisely which bytes successfully reached the cloud. It halts, keeps the remainder of the data safely queued, and waits for the next blip to resume exactly where it left off.
That is absolutely brilliant.
It is asynchronous magic. It mathematically guarantees that no critical data is lost due to timeout errors. It ensures that the absolute moment a microscopic crack of connectivity appears in the blackout zone, the most critical survival data automatically escapes to the outside world.
That drastically changes the coordination dynamic. Decision makers at the national level are not waiting days for a physical runner to hike out of a valley with a USB drive in their pocket. They are receiving highly structured data squeezed rapidly through whatever tiny cracks appear in the broken network. The Relay app alone justifies the procurement of the system.
It is a phenomenal safety net. However, we must confront the hardest, most brutal truth of emergency technology. You can design the most advanced Hotline module, you can deploy the most resilient store and forward Relay app, and you can buy the most expensive servers, but it is all completely, utterly useless if the local population does not know how to use it when the disaster actually strikes.
This highlights the fatal sociological flaw of emergency-only technology. If a government asks me to download a dedicated hurricane response app, I will likely only use it once every 3 years.
Exactly, if that.
By the time an actual hurricane hits, I will have forgotten my password, I won't understand the user interface, and I won't remember how to connect to the network. During a severe crisis, human cognitive load is maxed out. Panic sets in. People instinctively revert to what is deeply familiar to them. They try to use WhatsApp or standard phone calls, and when those fail, they just freeze.
You cannot force a population to learn a complex new digital workflow while the roof of their house is actively being torn off by a Category 5 wind. This behavioral reality is exactly why PBB fundamentally shifts away from being an emergency-only tool.
So what's the solution?
It incorporates a mandatory daily use strategy powered by a suite of localized everyday applications like Civitas, Tabulous, and Natalium.
And these are the applications designed to run exclusively on Machine 3, the daily app server we discussed earlier. The machine specifically dedicated to absorbing high-volume engagement.
Exactly. PBB must provide tangible, everyday value to the community during peacetime to ensure it works during wartime.
Let's look at the suite.
Civitas is a highly robust local community messaging application. It functions very similarly to a neighborhood WhatsApp or Viber group, allowing citizens to message each other, share photos, and organize community events. The massive appeal is that because it runs locally on the PBB network, it uses absolutely zero commercial mobile data. Citizens can chat indefinitely for free.
That's a huge incentive.
Tabulous is a gamified offline learning platform. It allows local governments to host interactive educational modules, disaster preparedness quizzes, and community announcements that citizens can engage with daily.
And Natalium.
Natalium is an incredibly practical local health center scheduling and management application, allowing citizens to interact with local health workers for routine care.
The strategy becomes remarkably clear. Instead of waiting for a catastrophic storm, a pregnant mother in the community uses the local PBB network every Tuesday to schedule her routine prenatal checkup through the Natalium module.
Right.
Teenagers in the neighborhood log on to the local Wi-Fi every afternoon after school to chat with their friends on Civitas because they don't have to spend money on cellular data load.
They interact with the system continuously, month after month.
It creates deep subconscious muscle memory. The psychological barrier evaporates. Because citizens are using the system daily to check health appointments or chat with neighbors, they instinctively know exactly how to open their phone settings and connect to the local PBB Wi-Fi. They remember their SSO login credentials because they used them yesterday. They are intimately comfortable with how the interface looks and feels. When the typhoon finally hits, the main grid collapses, and the cell towers fall, the citizens do not experience a jarring technological shock.
They do not have to read an instruction manual. They simply pull out their phone and perform the exact same mechanical actions they did on a calm Tuesday afternoon, naturally transitioning from daily modules to the emergency modules.
It is the ultimate Trojan horse for disaster preparedness. For a policymaker, this is perhaps the single most critical sociological insight of the entire architecture. You simply cannot train a population during a disaster. You must train them during peacetime.
The daily apps are not frivolous add-ons or municipal luxuries. They are the core adoption engine. They are the psychological bridge that ensures the emergency anchor actually sees utilization when lives are on the line.
The integration of physical hardware, localized network physics, and human behavioral psychology is incredibly compelling. We have a system that isolates failures, routes around blackouts, securely queues data, and trains its own users organically.
Yeah.
But I have to pivot to the harsh reality facing the mayors, the finance officers, and the procurement directors evaluating this.
The budget talk.
It's a fantastic vision, but traditional government IT procurement is infamous for bloated contracts, massive delays, and proprietary vendor lock-in. A decision maker listening to this is inevitably asking, this sounds incredibly complex. How on earth does a resource-strapped local government actually procure and pay for a multi-server, modular, offline-first network cluster without getting completely fleeced by a tech vendor?
That is the ultimate barrier to entry, and the creators of PBB recognize that if you try to sell this architecture using the traditional software licensing model, it will immediately fail in the public sector. Therefore, they engineered a revolutionary business model specifically designed to navigate the minefield of government procurement, the zero upfront software license concept.
Zero upfront software license. In a traditional model, a city wants to buy enterprise software, and the vendor demands a massive, multi-million-dollar capital expenditure right up front just for the right to use the code. You were saying PBB abandons that. Are they just distributing this sophisticated software framework for free?
It is absolutely not free, but the financial structure is entirely reoriented. PBB is not sold as a product. It is procured as a managed digital resilience utility. When a municipality adopts the PBB architecture, they are never hit with a massive, prohibitive upfront software license fee. The local government is not buying a permanent license key or intellectual property.
If there is no upfront software fee, how does a municipal procurement officer actually structure the contract? Public auditors demand extreme transparency. They require clear line items detailing exactly what the taxpayers are funding. They cannot approve a nebulous IT utility budget.
To ensure total audit safety and prevent the hidden costs that plague legacy IT projects, PBB utilizes a strict, highly transparent split-cost budgeting method. It mathematically deconstructs the deployment into 4 completely separate, easily auditable financial line items.
Let us examine these 4 lines closely.
Yeah.
If I am the finance director, what is line 1?
Line 1 is strictly hardware supply. This is purely a capital expenditure, or CapEx. This line item covers the physical procurement of the mini PCs for the 3-machine cluster, the enterprise routers, the PoE switches, the outdoor access points, and the battery backup systems. You are simply buying physical boxes at market hardware rates.
That is easily justifiable, tangible assets. I can send an auditor to the server room to count the physical boxes. What is line 2?
Line 2 is physical setup and labor. You must pay technicians or contractors to physically mount the antennas on the roof, run the weatherproof Ethernet cables through the walls, bolt the servers into the rack, and ensure the solar panels are securely mounted and wired to the UPS. This is straightforward manual labor and physical installation.
Again, highly tangible. I am paying for physical work performed. What is line 3?
Line 3 is software commissioning. Now, this is a one-time fee, but crucially, it is kept relatively small.
Why so small?
The reason it is inexpensive is because the PBB engineering team relies on highly automated setup kits. In traditional legacy IT, you have to pay a team of software engineers to sit in a room for 3 weeks, manually installing databases, configuring server environments, and writing custom routing scripts.
Which costs a fortune.
Exactly. PBB setup kits are designed to self-install the foundational software framework and automatically provision all the core modules, like map server, real-time, and hotline, with minimal human intervention. This line item merely covers the limited engineering time required to supervise that automated setup, securely download and cache the specific local map boundaries, and conduct the final stress test to prove the node is fully functional.
This structure isolates the costs beautifully. I have purchased the physical boxes, I have paid the labor to install them, and I have paid a minor fee to rapidly load the software framework onto them. The localized system is now alive and running. But you explicitly stated there was no massive upfront software license. If the initial commissioning fee is small, how does the organization maintaining the software survive financially? What is preventing a municipality from paying for the automated setup, taking the keys, and walking away? Where is the recurring revenue?
That brings us to the final and most critical component, line 4, the monthly managed node service fee.
There's a recurring cost. The subscription model. I need to push back on this on behalf of municipal finance officers. If the software does not have an upfront cost, why are we paying a monthly fee forever? Is the community simply renting the software, like a commercial streaming service? If a struggling municipality misses a payment during a budget shortfall, does the vendor remotely flip a switch and plunge the emergency room into darkness?
That is a vital concern, and the distinction must be clarified carefully. The monthly fee is intentionally designed to be incredibly modest. Think of it in relative terms as equivalent to a highly affordable daily operational expense. Roughly the cost of keeping a commercial coffee machine stocked for the office staff, but scaled to support an entire neighborhood node.
Okay.
Crucially, this fee is emphatically not a software license rental, nor is it a hostage situation.
If it is not a rental fee for the code, what exactly is the municipality buying every month?
They're purchasing a managed resilience utility. When a local government pays that modest monthly fee, they are sustaining the continuous, proactive maintenance of the entire ecosystem. They are funding ongoing network configuration tuning, critical cybersecurity patch deployments, continuous remote monitoring, and rapid troubleshooting support.
I see.
If an outdoor access point gets struck by lightning and goes offline, the remote support team sees the drop instantly. If a zero-day vulnerability is discovered that threatens the foundational software framework, the engineering team immediately pushes a secure patch to the local node.
So the municipality is not paying for access to the software. They're paying an operational expenditure, an OpEx, for an ongoing, highly specialized maintenance and monitoring contract.
Exactly. Here is the fundamental value proposition you present to a skeptical finance committee. You are not buying an app, you are funding the continuous operation of a digital public facility.
That's a great way to frame it.
Consider the physical Barangay hall or the municipal town hall itself. A government does not just pay a construction company to build the physical structure and then instantly fire the janitorial staff, the receptionist, and the security guards. A building requires a continuous budget for electricity, water, maintenance, and personnel to remain functional and safe. The PBB utility model applies that exact same logical standard to digital infrastructure. You are paying a predictable utility fee to keep the digital lights on and the digital doors open.
The shift from CapEx to OpEx makes incredible sense in this context. And frankly, this explains why public auditors and oversight committees would actually prefer this model. The graveyard of government IT is filled with municipalities that spent tens of millions of dollars on proprietary upfront software licenses, only to discover 3 years later that the software was never updated, the citizens never adopted it, the vendor went bankrupt, and the entire system is now useless shelfware.
It happens far too often.
With the PBB utility model, the financial risk is largely shifted away from the local government and onto the vendor. The city is paying a small, predictable monthly fee for an actively maintained service. If the node degrades, if the software bugs out, or if the system stops providing value, the service provider is legally obligated to fix it to maintain their contract. It perfectly aligns the financial incentives. The vendor only continues to get paid if the local system remains highly resilient and deeply useful to the community.
It represents a complete paradigm shift in public procurement. We are moving away from the risky practice of buying depreciating IT assets and moving toward the sustainable practice of procuring resilience as a guaranteed utility.
As we transition into synthesizing this massive journey we have taken today, the scope of what we have discussed is staggering.
We have deconstructed a profoundly complex architectural philosophy into its foundational physical and economic parts.
We certainly have. If you are a decision maker, a policymaker, or a local leader absorbing this, the macro-level takeaway is crystalline. Project Bantay Bayan represents a total rethinking of what civic infrastructure actually means in the 21st century.
Absolutely.
By mandating a strict 3-machine hardware standard, You physically isolate your emergency services, ensuring that casual daily use can never compromise your blast radius. By deploying a localized, offline-first network of routers, PoE switches, and point-to-point links, paired with intelligent localized DNS routing, you effectively become your own indestructible local ISP. By utilizing a robust, modular software framework that prioritizes store and forward data queuing and daily community apps, you guarantee that critical data escapes the blackout zone and that citizens build the muscle memory required to use the system instinctively. And finally, by adopting a transparent utility-based economic model, you protect your municipal budget from vendor lock-in while guaranteeing long-term maintenance. You are no longer waiting helplessly for the global cloud to save your community. You've literally built the capacity to bring the cloud home.
And while this specific architectural blueprint was forged in the incredibly demanding, disaster-prone crucible of the Philippines, an environment defined by devastating typhoons, complex archipelagic geography, and highly uneven commercial connectivity, its relevance is absolutely not limited to the developing world.
You view this as a highly exportable framework for global infrastructure.
Without question, the vulnerabilities of centralized cloud architecture are universal. Consider rural county governments in the American Midwest facing devastating tornado seasons that wipe out regional power grids. Consider isolated communities in the Australian outback confronting massive bushfires that melt physical fiber optic lines. Consider underserved or crisis-prone regions across Africa, South America, or even mountainous parts of Europe where the cellular grid is fragile. The Philippine model of localized, offline-first digital resilience is a blueprint that the entire modern world desperately needs to study and adapt.
It is a profoundly powerful vision, a localized innovation ready to redefine public safety on the world stage. As we conclude this deep dive, I want to leave you, the listener, with a final lingering thought to consider as you examine your own community's preparedness.
What's that?
Well, for the last century, we have historically judged the effectiveness of our civic leaders, our mayors, our governors, our utility commissioners, almost entirely on their ability to manage physical infrastructure. We judge them on their ability to keep the physical concrete roads paved, the physical bridges structurally sound, and the physical water reliably flowing out of the taps. But as our daily lives, our local economies, and our very survival during a crisis become completely and irreversibly dependent on digital coordination, as the global climate continues to change and the storms inevitably grow fiercer and more destructive, a new metric for leadership is emerging.
A digital metric.
Exactly. Will the defining test of future civic leaders no longer just be the state of their physical roads, but their proven ability to keep the local digital node alive when the global cloud inevitably fails?
It is the existential infrastructure question every modern leader must confront long before the next storm appears on the radar.
Something critical to think about. Until next time, stay curious and stay resilient.